picture this. It's 2019.
Okay.
And a gem dealer working out in the rugged, like heavily forested mountains of Myanmar finds this tiny grayish violet rock.
Just a little pebble, really.
Yeah, exactly. It weighs 1.1 carats, which, for context, is roughly the weight of a standard wire paperclip.
So practically nothing.
Right. It really doesn't look like much at all. But when this unknown little pebble makes its way to a high-tech laboratory, scientists do something just, well, extreme to it.
Oh, they go all out.
They place a microscopic fragment of it between the incredibly sharp points of two flawless diamonds, and they just squeeze.
Yeah.
They crank the pressure up to over 100,000 times the normal atmospheric pressure that you and I feel walking around right now.
I mean, it's the kind of crushing force you'd normally only find hundreds of miles deep within the Earth's mantle.
Right, and under that kind of localized, just apocalyptic stress, almost any normal crystal would just shatter into powder.
Oh, absolutely. It would be dust.
But this little violet rock didn't shatter. It mutated.
Which is wild.
Its atomic structure actually contorted into this highly compressed, like, superstructure, proving that the conditions required to initially forge it millions of years ago were unimaginably violent.
Yeah.
And in doing so, that tiny rock unlocked a 45-million-year-old story of a literal subterranean train wreck.
Which is such a beautiful paradox when you think about it.
How so?
Well, the most massive cataclysmic events in our planet's history, I mean, entire continents colliding, oceans being swallowed into the mantle, they are recorded most perfectly in the absolute smallest microscopic imperfections of the stones left behind.
That is mind-blowing. And welcome to today's deep dive, everyone. We are exploring the extraordinary intersection of microscopic analysis and macroscopic geological violence.
It's a fun one today.
It really is. Our mission today is to figure out how the tiniest flaws inside a gemstone act as, like, black box recorders for Earth's chaotic history.
Exactly.
And to guide us through this, conceptually at least, we are following the legendary career of gemologist johnkoivulaite.
A true giant in the field.
And we're unpacking the secrets of that bizarre mutating mineral I just mentioned, a mineral that was actually recently named in his honor.
To do this justice, we have pulled together an incredibly dense stack of research for you today.
We really have.
We are pulling directly from extensive notes from an accredited gemologist association, the AGA, an interview they did with Koivula himself.
Yeah?
We are dissecting detailed research papers and press releases from the Gemological Institute of America, the GIA. We also have these really comprehensive geological primers on Myanmar's Mogok stone tract from Lotus Gemology.
And serving as the absolute bedrock of our geological data today, we are going through an exhaustive PhD dissertation by Dr. Kayatho.
Oh, it's brilliant.
This dissertation is basically a masterpiece that painstakingly maps the complex igneous rock formations of that specific region in Myanmar. It's a total treasure trove of data.
It really is. And all of these sources, from the macrogeology mapping to the microscopic photography, they all converge on one central idea.
Which is,
if you want to understand the grand, sweeping narrative of the Earth, you cannot just look at the shiny, perfect surface. You have to look really, really closely at the flaws.
okay, let's unpack this. Because for the vast majority of human history, looking closely at flaws was the exact opposite of what the gem industry or jewelers or, like, royalty wanted to do.
Right. Flaws were bad.
Exactly. Which is why Koivula is such a fascinating figure to start with. We are talking about a man whose career spanned over 60 years, and he fundamentally inverted how science and commerce view precious stones.
He orchestrated a total paradigm shift. I mean, totally changed the game.
How did he even start?
Well, you can trace that shift back to his foundational training. He didn't come at this as a jeweler trying to sell a product.
Right.
He holds university degrees in both geology and chemistry from Eastern Washington University.
So he's viewing a rock not as a commodity, but as a chemical structure born from a geological process.
Exactly. He understands the structural formation of the Earth and the elemental building blocks that make it up. His early professional days were actually spent out in the elements as an exploration field geologist for Cominco American.
Oh, wow.
Yeah, he was doing macro-scale geological mapping, looking at the big picture of how landscapes fit together.
But his sources mention that the seed for his true life's work, the microscopic stuff, was planted way before he ever got a degree.
Oh, the childhood story.
Yeah. When he was a kid in North Bend, Washington, he found a quartz crystal. Now, if you picture a quartz crystal, you usually think of something clear or maybe a milky white.
Sure.
But this specific piece of quartz had something trapped inside it. pyrite inclusions.
Little chunks of fool's gold.
Exactly, just suspended inside the clear crystal. And that one childhood discovery just flipped a switch in his brain.
He became totally obsessed with the internal world of minerals, the things trapped inside. And when he eventually joined the Gemological Institute of America in 1976, he brought that obsession with him.
Which was weird for the time, right?
Yeah, completely. To understand how radical his approach was, you have to realize that before Koivula, inclusions, these tiny bits of alien material or trapped fluids or little crystals stuck inside a larger gem, they were considered nuisances.
Just ugly marks.
Yeah, the industry called them flaws, and their only function was to hurt the commercial value of a stone. A clear stone was a good stone. A stone with stuff in it was a bad stone.
So a jeweler looks at a ruby with a weird little crystal inside and thinks, man, this ruins the clarity. I have to discount this.
Right.
But Koivula walks in and says, you had this completely backwards. That flaw is a diagnostic signature.
He proved that those inclusions are basically nature's fingerprints.
Okay.
By analyzing the chemistry, the shape, and the orientation of those trapped internal features, Koivula demonstrated that you can determine a gem's natural origin.
Wow.
You can pinpoint its exact geographical birthplace down to the specific valley it was mined from. And most importantly, for the modern market, you can prove whether a stone is natural or if it has been artificially treated or grown in a lab.
I keep thinking about this like a crime scene.
Okay, let's hear it.
Imagine a forensic investigator walking into a room where a robbery happened. The local cops are complaining about this annoying smudge on the security camera lens that ruined the footage of the room.
Right.
They're ready to throw the tape away. And the investigator looks closer and realizes, wait a minute, that smudge on the lens is the fingerprint of the culprit. The thing you thought was ruining the picture is actually the only piece of evidence that can solve the mystery.
That captures his contribution perfectly. He took the smudge and turned it into the central pillar of modern gemology.
That's so cool.
But he didn't just hoard this knowledge. He spent decades meticulously documenting it so the rest of the world could see what he saw.
Right, the books.
Yeah, he teamed up with Dr. Edward J. Gubelin to co-author the Photoatlas of Inclusions in Gemstones. And this isn't just a casual coffee table book.
No, it's massive.
It is a monumental 3-volume masterwork. Volume 2 alone contains over 2,200 color plates of these microscopic internal landscapes. It established the visual and scientific baseline for the entire global industry.
But here's the technical hurdle that the sources bring up, and I find this fascinating. To get those photos, to even see these microscopic fingerprints clearly in the first place, he had to completely change the tools the industry was using.
For lighting.
Specifically, the lighting, yeah. The AGA interview highlights his introduction of fiber optic lighting to the Gemological lab. Now, on the surface, fiber optics sounds incredibly simple. It's just light traveling through a glass tube.
Right.
Why was this such a massive game changer? What was everyone else using before this?
Well, they were using traditional incandescent lighting. Think of the old school filament light bulbs.
Really, once they get really hot.
Exactly. The problem with incandescent lighting is that it generates a tremendous amount of heat as a byproduct of the light. Now, put yourself in the shoes of a microscopist. You are examining a delicate crystal, perhaps one that already has internal stress fractures. You put it under the microscope and blast it with intense, direct, incandescent heat.
You're basically baking it while you look at it.
You are. And that thermal shock can actually damage the specimen. It can cause a valuable gem to fracture right there on the microscope stage.
Oh, that would be a bad day at work.
A very expensive mistake. Furthermore, from an optical standpoint, traditional incandescent light is often too broad and too diffuse. It floods the stone, washing out the incredibly subtle, deep internal features you are trying to find.
It's like trying to read a faded, low-contrast pirate map by holding it up to a blazing bonfire.
That's a great way to put it.
The sheer volume of the light blinds you to the delicate ink strokes. You'd be much better off using a small, highly targeted LED flashlight.
And that targeted flashlight is exactly what Koivula championed with cool, flexible fiber optic lighting, because the light source, the actual bulb generating the illumination, is physically separated from the output by those long glass fibers.
Yeah.
So it delivers intense, brilliant light without transferring any of the destructive heat. But the real magic is the flexibility.
How so?
Because the fiber optic wands are bendable cables, you can manipulate them by hand. You can provide oblique side lighting. You can graze the light across a specific internal plane to create shadowing.
You can control the angle at incidence perfectly.
Exactly.
And that specific technique, that ability to cast a shadow across a microscopic flaw, revealed things that were completely invisible under floodlights. The AGA interview notes highlight a massive victory for Koivula using this exact method regarding Kashan synthetic rubies.
Oh, the Kashan rubies. That was huge.
Let's dig into that because the stakes were incredibly high for the gem market at that time.
The stakes were existential for the ruby market. Kashan rubies were early laboratory-grown synthetics developed in the 1970s and 80s, and they were terrifying to the industry because they were notoriously difficult to distinguish from natural rubies. They didn't look like cheap glass fakes. They looked like flawless, top-tier natural stones.
Because they technically are rubies, right? Chemically speaking.
Chemically, yes. They are aluminum oxide with chromium, but the way they were made in the lab left a very specific, almost invisible trace.
Okay, what was it?
You see, to grow a ruby, you have to melt the ingredients, but the melting point of aluminum oxide is incredibly high. So the laboratories use a flux.
A flux.
Yeah, a chemical solvent, often containing lead or molybdenum, that acts like a catalyst to significantly lower the melting point, allowing the ruby crystals to grow in a molten bath at manageable temperatures.
Okay, so the ruby is growing inside this chemical soup.
Exactly. And as it grows, it occasionally traps microscopic, irregular remnants of that flux bath inside its crystal lattice.
Oh, I see where this is going.
But these remnants are incredibly wispy, almost transparent. Under standard incandescent lab lighting, the intense red color of the ruby would completely overpower them. You couldn't see the flux. They looked flawless.
Until Koivula takes his fiber optic wand, turns off the main overhead light, and shoots a cool beam of light into the ruby from an oblique side angle.
Exactly. When he grazed that fiber optic light across the interior of the stone, those wispy, trapped remnants of the chemical bath suddenly caught the light, contrasting against the dark background.
Wow.
It looked like tiny, glowing dust motes caught in a sunbeam in a dark room. Koivula described them as looking like microscopic rain.
Microscopic rain, that's poetic.
And just like that, the industry had a smoking gun. If you saw the microscopic rain, you knew the stone was grown in a laboratory flux bath, not inside the earth.
He used a similar light trick to expose another massive scandal too, right? Lead glass-filled diamonds. I know he worked with Robert Camerling on this.
Oh, the lead glass treatment was insidious.
What did they do?
Unscrupulous dealers would take a lower quality diamond that was full of surface-reaching fractures, cracks that made the stone look cloudy or white.
Okay.
They would force high refractive index lead glass deep into those cracks under high heat and pressure. Because the glass bent light in a similar way to the diamond, the cracks effectively disappeared to the naked eye.
That's basically fraud.
Totally. A heavily fractured, low-value stone suddenly looked like a premium, high-clarity diamond.
But Koivula and Camerling figured out that if you manipulate the lighting, casting it down the precise plane of the hidden fracture, the lead glass reacts differently than the host diamond.
It does. It produces a diagnostic flash effect.
A flash effect.
Yeah. The filled crack will suddenly flash with bright, unnatural colors, often vivid blue or orange.
It was a monumental breakthrough for market transparency. The dealers could no longer hide the treatments.
He essentially saved the industry from itself during an era when technology for synthesizing and treating gemstones was rapidly outpacing the traditional tools used to detect them.
Which is incredible. Oh, and before we move on to his ultimate legacy, I have to throw in this fun fact from the GIA press release.
I love this fact.
Because of his unparalleled expertise in chemistry, geology, and microscopy, he was actually hired as the scientific and technical advisor for the TV series MacGyver. And he won first place in Nikon's Small World Photomicrography competition in 1984. The guy isn't just a scientist. He's an artist and a pop culture touchstone.
His impact is remarkably broad. But, within the scientific community, his contributions to mineralogy are viewed as so foundational that they eventually decided to grant him the ultimate geological honor.
Right.
You can win awards, you can write books, but there is only one way a geologist achieves true immortality.
You get a rock named after you.
Yeah.
And not just a local nickname. In 2019, the International Mineralogical Association officially recognized a brand new, never-before-seen species of mineral and named it johnkoivulaite.
Yes, johnkoivulaite.
So how does a brand new mineral just show up? Where do you even find something that no human being has ever cataloged before?
This is where our story shifts from the high-tech laboratories in California to the rugged, remote mountains of Myanmar, specifically the Painite mining area of the Mogok Valley.
According to the GIA research paper, this discovery started with a local gem dealer named Ne Mayo. He was sorting through rough stones and found this single, unidentified 1.16 carat crystal. It had a strange grayish-violet color. He couldn't figure out what it was.
He was stumped.
Yeah, it didn't test like a Sapphire or a Spinel or any of the usual suspects. So he sent it to the GIA for analysis. The lab technicians run their spectrometers on it, look at the data, and realize this isn't just a rare stone, it is structurally unique.
Utterly unique.
The GIA purchases the tiny crystal for their museum, and that initiates the grueling process with the International Mineralogical Association to get it officially recognized.
It's important to understand how rigorous that process is, by the way. You can't just find a piece of quartz that happens to be an unusual shade of pink and demand a new name for it.
Right, there are rules.
Very strict ones. To be classified as a new mineral species, the specimen must possess a distinct, unique chemical composition and a specific crystal structure that has never been documented in nature.
Okay.
After exhaustive testing, they determined that johnkoivulaite is the 7th recognized member of the beryl group.
Okay, the beryl group. So if you are listening and you own an emerald or an aquamarine, you own a beryl. This new violet rock is a cousin to those gems.
Structurally, yes. Beryl is a cyclosilicate.
A cyclosilicate, okay.
If you could zoom in and look at its atomic architecture, it has a hexagonal crystal framework. Picture a microscopic tower made of stacked rings, where each individual ring is constructed from 6 silica tetrahedra linking together.
Like a tiny honeycomb tower.
Exactly. That is the fundamental baseline architecture of any beryl. But johnkoivulaite takes that basic blueprint and introduces some incredibly complex, heavy elemental substitutions that force the architecture to bend to its will.
Let's get into the chemistry of that, because I have the formula right here from the Caltech analysis, and it looks like an algebra equation gone wrong.
It is a mouthful.
It is CS, then B to B in parentheses, Mg2Si6018.
Yeah, let's break down what that formula actually represents physically, because it explains why this mineral is so alien.
Please do.
In a standard, common, beryl-like, your everyday emerald, you have beryllium atoms occupying very specific tetrahedral sites in that crystal lattice, and aluminum atoms occupying what are called octahedral sites. Those are the standard building blocks.
Okay, beryllium and aluminum.
But in johnkoivulaite, the environment it grew in was so weird that it forced different elements into those slots. Boron partially substitutes for the beryllium in the tetrahedral sites. Then magnesium swoops in and completely replaces the aluminum in the octahedral sites.
That accounts for the middle of the formula. But what about the C's sitting right at the front? That stands for cesium, right?
Yes, cesium.
But cesium atoms are massive compared to beryllium or magnesium. How do they fit into the structure?
They are very large alkali metal atoms, and you're right, they don't fit into the standard lattice slots. They are too bulky.
So where do they go?
Instead of replacing a structural beam, those massive cesium atoms stuff themselves into the structural channels. Remember those stacked silica rings we visualized earlier?
Yes, honeycomb tower.
Yes. They form a hollow tube running down the center of the crystal. The cesium atoms get rammed down into those hollow tubes, acting almost like a heavy pillar holding the rings in place.
But this brings up a fundamental question. If it still has that basic hexagonal ring structure of an emerald, why does swapping out some beryllium for boron and shoving some cesium down the middle make it an entirely new species?
It's a fair question.
Why isn't it just classified as a boron-rich emerald or a weird violet beryl? Where's the line drawn?
The line is drawn at structural distortion. A mineral is defined by a specific chemical composition residing within a specific structure.
Okay.
When you force boron to take the place of beryllium, it fundamentally alters the unit cell parameters. That means the actual physical dimensions, the bond lengths, and the volume of the crystal lattice have to stretch and warp to accommodate the new element.
So it's physically changing shape.
Yes. The electrical charge is balanced differently. It is no longer just a trace impurity like the tiny sprinkle of chromium that turns a regular clear beryl into a green emerald. In an emerald, the chromium is just a guest in the house. In johnkoivulaite, the boron and magnesium are load-bearing walls. They are essential structural components. If you removed them, the mineral would collapse. It wouldn't exist in this form. That is what crosses the threshold into a new species.
And because the internal architecture is so warped by these heavy elements, it creates some truly wild physical properties that you can see with the naked eye. The GIA paper highlights its intense pleochroism.
Oh, its pleochroism is amazing.
Now, we've talked about color-shifting stones before, but this is extreme.
Pleochroism is an optical phenomenon where a single crystal appears to be completely different colors depending on the angle you view it from. specifically as light interacts with its internal structure.
Right, and usually people compare this to wearing polarized sunglasses, but I don't think that does it justice. Sunglasses just block glare. Looking at johnkoivulaite is more like looking at one of those lenticular printed pictures, the plastic rib bookmarks you had as a kid, where if you tilt it one way, it shows a dinosaur, and if you tilt it the other way, it shows a spaceship.
I remember those.
The object itself physically appears to change state just by altering your viewing angle.
That lenticular analogy is much more accurate for what is happening inside the crystal. It's because johnkoivulaite is what gemologists classify as uniaxial negative.
Uniaxial negative, meaning
In simple terms, this means that light travels through its warped hexagonal lattice at different speeds depending on which axis it is moving down. The light physically splits.
wow.
The ordinary ray of light, which vibrates perpendicular to the main optical axis, passes through the crystal structure with relatively little interference. When you view the stone from that angle, it appears nearly colorless, just clear glass.
But when you tilt the stone and look down the other axis,
You engage the extraordinary ray. This light vibrates parallel to the main axis, and as it travels down that path, it interacts intensely with the iron and magnesium atoms embedded in the lattice.
okay,
Those atoms selectively absorb certain wavelengths of the visible spectrum, and the light that survives and reaches your eye appears deep, saturated bluish violet. So as you turn the crystal in your hand, it snaps from clear to violet and back again.
it's an optical magic trick built right into the atomic structure.
It really is.
The sources also mention it has a refractive index of 1.608 and a hardness of 7.5 on the Mohs scale, which means it is quite durable, easily capable of scratching window glass.
It's a tough little rock.
But then the GIA paper details a test they performed on it that sounds less like geology and more like medieval torture. They put it in a diamond anvil cell. You touched on this in the introduction, but we need to explain how this actually works.
The diamond anvil cell is a staple of high-pressure physics. The goal is to simulate the extreme pressures found deep inside the Earth or on other planets. The device itself is surprisingly small, but it leverages geometry.
Oh, so
You take two tiny, flawlessly cut diamonds. You use diamond because it is the hardest known natural material. Anything weaker would just deform under the stress. They machine the tips of these diamonds flat, creating tiny surfaces called culettes.
and then they put the microscopic sample of johnkoivulaite between those two flat diamond points.
Exactly. They actually place a thin metal gasket between the diamonds, drill a microscopic hole in the gasket, place the sample inside that hole along with a pressure transmitting fluid, and then they mechanically force the two diamonds together.
Like a vice.
Yes, but because the force is being applied to such an infinitesimally small surface area on the diamond tips, the pressure skyrockets exponentially.
The paper states they compressed it to 10.2 GPa, gigapascals.
That's a massive number.
To give you some context on how insane that number is, one single gigapascal is roughly 10,000 times the atmospheric pressure at sea level. So 10.2 GPa is over 100,000 times the pressure we feel standing on the surface of the Earth.
It's hard to even conceptualize.
It is the equivalent of taking hundreds of fully grown elephants and balancing all of their weight on the tip of a single stiletto heel.
The forces are apocalyptic, and what the researchers were looking for was the breaking point.
Right.
At what pressure does the crystal lattice of johnkoivulaite finally fail? At what point do the atomic bonds snap and the mineral amorphize or turn into glass? But the fascinating thing is, it didn't snap.
Yeah.
As the pressure mounted toward 10.2 GPa, the lattice didn't break. It shifted.
It mutated into that superstructure we talked about.
Yes, the immense pressure forced the atoms to physically displace and slide into new, tighter configurations. The symmetry of the crystal fundamentally changed. And in this new, distorted state, the mineral actually became twice as compressible as it was initially. It adapted to survive the pressure.
Which leads us directly to the great mystery of this entire deep dive. If this mineral requires that kind of apocalyptic pressure to mutate, and it requires this incredibly rare soup of heavy elements, boron, cesium, magnesium to form in the first place, well, where on Earth could such a bizarre crystal naturally come from?
Right.
You can't just bake this in a standard geological oven. You need a geographical blender of catastrophic proportions.
And that blender has a name. To geologists and gemologists alike, it is a region of almost mythical status. We have to travel to the Mogok Stone Tract.
Let's set the scene for the listener. If you were to travel to Mogok, you would head to the Mandalay province in Myanmar, about 200 kilometers northeast of the city of Mandalay.
Beautiful area.
The local Shan language refers to the area as Mungkut, which translates to the Winding Valley. The Lotus Gemology primer describes the physical landscape as a sickle-shaped, mountainous amphitheater. It is a closed-off, incredibly rugged terrain.
Very rugged.
And hiding beneath that terrain is arguably the richest, most densely concentrated pocket of mineral wealth on the entire planet.
The sheer variety of gems pulled from this one relatively small area defies logic. It's not just johnkoivulaite. For centuries, Mogok has been famous for producing the world's finest pigeon's blood rubies.
The best of the best.
But it also produces spectacular red spinels, deep blue sapphires, vivid green peridot, ethereal moonstone, topaz, and painite.
Painite is wild. For a long time, the Guinness Book of World Records listed painite as literally the rarest mineral on Earth. There were only 2 known crystals in existence for decades, and they came from Mogok.
Over 50 distinct gem species are mined in this one concentrated valley. It's like nature emptied her entire jewelry box in one spot.
But to understand why this one valley is packed with such an absurd variety of rare chemistry, we have to zoom out, way out. We have to stop looking at the valley and start looking at the continents. We need to talk about orogenic belts.
Orogeny, mountain building events. The Earth's crust is not static. It is made of massive tectonic plates that float on the semi-molten mantle. When these plates collide, the crust buckles, folds, and pushes violently upward, creating mountain ranges.
Like a slow-motion car crash.
Very slow, but the mountains you see on the surface are just the aftermath. Deep underground, the immense stress, friction, and heat of 2 continents grinding together create fantastic zones of mineral formation. Millions of tons of rock are recycled through metamorphism. Mundane, everyday minerals are subjected to so much heat and pressure that their atomic bonds break and reform into crystalline wonders.
Now, the Lotus Gemology primer points out a really interesting timeline. Most of the world's greatest ruby and sapphire mines, the places that supply the global jewelry trade, fall into one of 2 major orogenic events.
Right.
The older one is the Pan-African orogeny, which happened roughly 750 to 450 million years ago. That ancient continental collision created the deep gem deposits we mine today in places like Kenya, Sri Lanka, and Madagascar. Those stones have been sitting in the dark for over 500 million years.
But Mogok is different. Mogok is a product of the Himalayan orogeny. This is a much younger geological event. It occurred just 45 to 5 million years ago.
Which sounds like a long time to a human, but 45 million years ago in Earth time is practically last Tuesday. It's incredibly recent.
It is recent, and it was violently fast in geological terms. The scientific literature often describes the Himalayan orogeny as a continental train wreck. Let's visualize this.
Okay.
About 50 million years ago, the Indian subcontinent had broken off from the ancient supercontinent of Gondwana. It was an island, and it was speeding north across the ocean at geological warp speed. And directly in its path was the massive Eurasian plate.
It didn't just gently bump into Asia and stop. It rear-ended the continent at full speed.
The Indian plate smashed into Eurasia with so much momentum that it didn't just crumple the edge, it drove down and shoved itself some 2,000 kilometers underneath Central Asia, lifting the Tibetan Plateau and creating the Himalayas.
And this subduction, this dragging of material deep underground, is where the alchemy of Mogok begins. Because before India hit Asia, there was a massive body of water between them, the Tethys Sea.
Yes, the Tethys.
And like all oceans, the Tethys was teeming with life for tens of millions of years. Sea creatures, corals, microscopic plankton. As these organisms live and die, their calcium-rich shells and skeletons drift to the bottom of the ocean. Over eons, all that calcium and carbon builds up into a massive, thick layer of pale sedimentary rock on the seafloor. Pure limestone.
Now imagine taking that massive layer of ancient limestone seafloor, catching it between the jaws of 2 colliding continents, and dragging it deep down to the Earth's crust.
That's horrifying.
Dr. Koivula's dissertation provides the exact parameters of this subterranean forge. He calculated that this limestone was dragged down to a depth where the temperatures reached 600 to 650 degrees Celsius under a pressure of 4.5 kilobars.
You are literally baking the remains of an ancient ocean in a high-pressure oven.
And under that immense heat and pressure, the limestone undergoes high-grade metamorphism. The calcium and carbon atoms vibrate furiously, their bonds break, and they recrystallize. The soft, chalky limestone transforms into hard, crystalline marble.
Okay, so limestone becomes marble.
But what makes the Mogok marble unique is the grain size. It is characterized by being extremely coarse-grained. If you look at it, the individual calcite and dolomite crystals within the rock body are quite large.
The grain size is a direct indicator of time,
Right,
right?
yeah, okay.
If molten rock erupts from a volcano and cools instantly in the ocean, it turns into obsidian glass with microscopic grains. But if this marble is cooling very, very slowly, deep underground, insulated by miles of crust over millions of years, the crystals have time to gather material and grow large and perfectly ordered.
That is the key. That exceedingly slow cooling and crystallization process deep underground is the exact reason why Mogok produces gems of such singular large size and structural perfection. But having the gems trapped inside a solid block of marble buried miles underground doesn't help us. To understand how we actually get to the gems today, we have to look at how that marble is weathered once tectonic uplift pushes it to the surface.
This brings us to the visual landscape of Mogok today, and it's startling. If you go to the Mogok Valley, you don't just see rolling, grassy hills. You see these eerie, jagged, black rock pinnacles rising straight up out of the green jungle valleys like dragon's teeth.
It looks like a matte painting from a fantasy movie.
Geologists call this karst topography.
Karst topography develops in landscapes underlain by highly soluble rock. In this case, the coarse-grained marble. Marble is hard, but chemically, it is still calcium carbonate. Over millions of years, mildly acidic rainwater water that has picked up carbon dioxide from the atmosphere and soil washes over these mountains. It acts as a slow, weak solvent. It literally dissolves the weaker calcium carbonate of the marble, etching away the rock face, leaving behind those jagged, insoluble black pinnacles.
And more importantly, it riddles the ground beneath the surface with a vast network of caves, sinkholes, and narrow underground drainage passages.
And here is the genius of nature's design. As that weak marble is slowly dissolved by the acid rain, it disintegrates, but it leaves behind the things that can't be dissolved.
So gems.
The extremely hard, chemically durable gemstones that were baked into the marble, they are free from their rock prison. Gravity and water wash these heavy gems down into the bottoms of the caves and sinkholes. The local Shan miners call these natural underground catch basins Ludwin.
So these Ludwin caves act like an immense geological panning system. Over millions of years, the water dissolves away the worthless host rock and concentrates the heavy, precious gems into accessible, highly rich pockets just waiting in the dark to be scooped up.
It's an incredible sorting mechanism.
Oh, wait, I have to stop here because there is a glaring hole in this logic that we haven't addressed. Let's look at the chemistry again.
Let's do it.
We established that the host rock was pure limestone from the bottom of an ancient sea. Limestone is just calcium, carbon, and oxygen. The heat turned it into marble. Still just calcium, carbon, and oxygen. But rubies, chemically speaking, corundum, are made of aluminum and oxygen with a dash of chromium to give them that pigeon's blood red color.
Correct.
How does a pure calcium carbon marble rock suddenly grow aluminum oxygen rubies? Where do the missing ingredients come from? I mean, you can't bake an apple pie if you only have flour in the kitchen, no matter how hot the oven gets.
That is the crucial question. It is the exact puzzle that has kept the geology of Mogok so heavily debated and scrutinized for decades. Because you are entirely correct, the standard model for Himalayan marble, the idea of a closed system where everything needed to make the gem was already present in the original sedimentary rock, completely fails in Mogok.
Right, the ingredients aren't there.
Pure limestone does not contain aluminum or chromium. Those missing ingredients had to be introduced from an external source while the rock was baking.
And this brings us to a wonderfully messy, highly dynamic geological process called metasomatism.
Metasomatism is essentially the chemical alteration of a solid rock by the injection of hydrothermal fluids. In the case of the Mogok rubies, geologists theorize that during the tectonic collision, extreme pressure squeezed water out of neighboring rock formations.
Okay.
Specifically, hot, mineral-rich watery solutions flowed out from ancient metamorphosed clay shales in nearby margin basins. These superheated fluids acted as a delivery system. They carried the dissolved aluminum and chromium from the shales and permeated the porous, heated marble.
So it's literally a chemical injection from next door. But even with the aluminum and chromium arriving in the marble, it's not a guarantee that a ruby is going to form. There is a brutal chemical battle going on inside the rock for those resources.
Oh, it's a very fierce one. Because the marble in Mogok isn't always pure calcite. Often it contains high amounts of dolomite, which means there is a significant amount of magnesium present in the rock matrix.
And magnesium complicates things.
Big time. If there is magnesium present when those hot aluminum and chromium-rich fluids arrive, The elements will preferentially bind with the magnesium first. The chemistry favors it. And when magnesium, aluminum, and oxygen bind together, they do not form a ruby, they form a completely different gemstone. Spinels.
Spinel, which, to be fair, is a gorgeous gem in its own right. The sources mention the spectacular red spinels found in Mogok. They form as these perfect octahedral crystals that look like two tiny pyramids glued base to base.
They are beautiful.
The local miners call them netui, which translates to angel polish because they come out of the dirt with faces so flat and shiny they look like they were cut by a master jeweler.
They are stunning, and historically, many of the famous rubies and European crown jewels actually turned out to be Mogok spinels upon modern testing. But from a chemical standpoint, the spinel is the mortal enemy of the ruby.
The mortal enemy, I love that.
Spinel is a glutton. It will gobble up all the available aluminum and chromium from those hydrothermal fluids as long as there is even a trace of magnesium left in the rock. It is only when the magnesium in the local marble is entirely exhausted, when the spinel has eaten it all up and stopped growing, that the remaining aluminum and oxygen can finally bond together to form corundum, a ruby.
The ruby is the leftover product of a chemical battle it usually loses. That perfectly explains why the Lotus Gemology primer specifically notes that Mogok produces far more red spinels than rubies. The conditions for ruby require the complete starvation of magnesium.
Yes. But even metasomatism, these fluids leaking from ancient shales, doesn't explain everything we find in the Winding Valley. It doesn't explain how you get massive cesium atoms.
Right, back to johnkoivulaite.
Exactly. It doesn't explain the boron in johnkoivulaite or the extreme rarity of calcium, zirconium, or borate painite. Shales don't carry those exotic elements in high concentrations. For that, we have to introduce a much more violent, highly localized geological mechanism.
Skarn. Skarn. It sounds aggressive. What exactly is a skarn event?
Think of skarn as a highly volatile contact zone, a chemical forge. It occurs when an intrusive igneous rock, like a superheated molten magma pushing its way forcefully up from the Earth's mantle, smashes directly into a cooler, solid, carbonate rock, like our Mogok marble.
So you have a magma blowtorch hitting a block of calcium. Two completely different chemical systems. One molten and aggressive, the other solid and stable, mashed together under extreme heat. It bakes an entirely new menu of rare minerals right at the boundary line where they touch.
That is precisely what skarn is. And this is where Dr. Kayathu's PhD dissertation becomes so incredibly valuable. He didn't just theorize this, he hiked the mountains and mapped the exact locations of these forges in Mogok.
Amazing.
He details intense, late-stage magmatic intrusions that punched violently up into the Mogok Metamorphic belt millions of years after the initial continental collision. He dated them.
What are the dates?
We have the Kabayang granite, a biotite microgranite that intruded roughly 15 to 16 million years ago. We have cyanitic rock intrusions dated at 25 million years ago, and leucogranite intrusions dated at 32 million years ago.
Multiple waves of magma pushing up over tens of millions of years. And his data notes the depth of these specific emplacements ranges from the catazone to the mesozone. Now, for the non-geologists listening, let's translate that.
Sure.
The catazone is the deepest, hottest zone of metamorphism.
Sure.
Right? It's so hot and under so much pressure that the rock doesn't even fracture. It essentially deforms and flows like thick plastic. While the mesozone is slightly shallower, a bit cooler, where rocks can still fracture and fault, creating spaces for veins to form.
Exactly. And Dr. Kayathu provides one more vital piece of chemical data. He calculates that the region's Peacock index is 55.
Okay, an index of 55. What does that actually mean in plain English? Why does that number matter to the gems?
Think of magma as a giant, complex, molten batch of soup. The Peacock Index, or Alkali Lime Index, is essentially a geological taste test. It's a classification system that measures the exact point in the magma's cooling process where two specific flavor profiles, the alkalis, like sodium and potassium, and the calcium, are in perfect balance relative to the silica content.
Okay.
An index of 55 means this particular magma soup was incredibly rich in both those volatile alkalis and calcium. It sits right on the boundary line, classifying the region as calcic to alkalic calcic.
So it's a very specific, highly reactive recipe. And crucially, these late-stage granitic magmas were carrying volatile exotic elements up from the mantle that simply aren't found in normal marble or shale. Elements like zirconium, cesium, and boron.
Right. And when that volatile, boron-rich granite hits the calcium-rich marble, the skarn reaction triggers the growth of wildly improbable minerals that require both systems to exist.
Give us an example.
The sources point to a very specific, mind-blowing example, the Wetlu mine. Dr. Kayothu's mapping shows that at Wetlu, a 32-million-year-old leucogranite intrusion smashed into a specific layer of diopside phlogopite marble. At that exact highly localized contact zone, the literal boundary line where the rocks melted together, the elements mixed to create painite.
The rarest mineral on Earth, birthed at a microscopic boundary line between two colliding rock types deep underground. But the American Museum of Natural History research paper notes something even more incredible that was found at the Wetlu mine. They found specimens of rubies that had crystallized directly on top of the painite crystals. They were fused together.
Which is a massive revelation for geologists. It proves beyond a shadow of a doubt that corundum growth, the formation of the rubies, was happening simultaneously with this volatile Starn event.
Wow.
The rubies weren't just forming slowly from distant shale fluids seeping in. They were being actively forged by the violent, localized interaction of the granite magma burning into the marble.
But this sheer variety raises a practical question. The sources mention different mines produce totally different things. The Balmar mine produces sapphires. Wetlu has painite. How do the local miners actually know where to dig?
It's a skill for sure.
If the valley was subjected to an ocean subduction, metamorphism, metasomatism from shales, and 3 different waves of magma intrusions over 40 million years, isn't the underground just a chaotic blender? Are the miners just digging blind into a massive geological leftovers dump and hoping for the best?
It sounds chaotic on a macro scale, like a blender, as you said, but on a micro scale, it is incredibly structured. The chemistry is strictly bound to the rock type, and the local Shan miners understand this stratigraphy implicitly, even if they aren't publishing PhD dissertations on the Peacock Index.
They know the land.
They read the rocks. The geological mapping shows precise host rocks for different gems. If a miner wants to find rubies or spinels, they track the white marble layers and the Ludwin caves beneath them. If they want sapphires, they ignore the marble and look for the intrusive syenite or pegmatite veins.
And if they want peridot, that beautiful, vivid green gem, they have to find a completely different environment altogether. The sources describe the Mia Saintong mine area as hosting peridotite and dunite rocks.
Very different rocks.
These are ultramafic rocks, meaning they are incredibly dense, dark, and rich in iron and magnesium, usually originating straight from the upper mantle. And the miners look for very specific pocket-type deposits within these rocks, which they locally call B.O.O.G, to find the peridot crystals. So they aren't digging blind at all. They're reading the rock types like a treasure map.
They are reading a very complicated map. The Mogok stone tract defies any simple single-origin explanation. Geologists often compare it to a palimpsest, an ancient manuscript that has been written on, erased, and written over again multiple times.
That's a great analogy.
You have the ancient crustal foundations, overwritten by the massive Himalayan oceanic collision, which beaked the marble, which was then overwritten again and again by multiple waves of igneous granite intrusions burning through the rock over tens of millions of years.
In this mind-boggling macroscopic complexity, the tectonic crashes, the oceanic subductions, the magmatic blowtorches, the millions of years of slow acidic rain weathering. This is precisely why the microscopic work of John Koivula is so vital. We have to bring the narrative full circle here. We're connecting the cataclysmic violence of Mogok to the quiet, cool, fiber-optic light of Koivula's microscope.
The connection is absolute, because every single one of those violent macroscopic events we just described is perfectly durably recorded as a tiny time capsule inside the gems themselves. When you look at an inclusion through a microscope, you aren't just seeing a flaw. You are looking at a direct snapshot of a geological process that occurred 45 million years ago at 600 degrees Celsius and 4.5 kilobars of pressure.
The sources specifically mention 3 types of inclusions that act as these recorders: fluid inclusions, two-phase inclusions, and rutile needles. Walk us through what exactly those are telling us.
Let's start with a fluid inclusion. When a crystal like a sapphire is growing deep underground in that highly pressurized, hot environment, it isn't growing in empty space. It is surrounded by fluids, either hydrothermal water leaking from the shales or liquid magma from the granite intrusions. Occasionally, as the crystal lattice builds itself layer by atomic layer, it accidentally closes over a microscopic droplet of that surrounding fluid, trapping it inside the solid gem forever.
So you are literally looking at a microscopic drop of water from an ocean or a magma chamber that hasn't existed for 50 million years. It's perfectly sealed.
It is a pristine sample of the ancient Earth, and it gets more complex. Sometimes, as that trapped fluid cools down and contracts over millions of years, the liquid shrinks faster than the solid cavity holding it. This creates a tiny vacuum bubble of gas inside the liquid droplet.
A two-phase inclusion.
That is a two-phase inclusion, a liquid and a gas trapped together. By analyzing the ratio of gas to liquid and the chemical makeup of the fluid, modern scientists can reverse engineer the exact temperature and pressure the rock was experiencing at the exact moment the gem formed.
That is incredible. What about the rutile needles? The GIA uses those constantly to determine if a sapphire has been heat-treated.
Rutile needles are microscopic, hair-like crystals of titanium dioxide that intersect at 60 and 120-degree angles inside a gem, creating what jewelers call silk. Their presence tells us a lot about the cooling history of the stone. They form through a process called exsolution.
Let's define exsolution without the jargon. How does that work?
Imagine making a cup of hot tea and stirring in a ton of sugar. When the tea is very hot, the sugar dissolves completely into the liquid. It's a single, uniform solution. You can't see the sugar at all. But what happens if you put that supersaturated tea in the fridge and let it cool down?
The liquid can't hold all that sugar anymore, so the sugar crystallizes and settles at the bottom of the glass.
That unmixing of a solution as it cools is exsolution. Inside the Earth, when a sapphire forms at 650 degrees Celsius, it absorbs titanium atoms into its crystal lattice, much like the hot tea holding the sugar. But as the Himalayan mountains uplift and the rock very slowly cools down over millions of years, the sapphire lattice contracts and forces the titanium atoms out. They unmix.
Ah, I see.
But because they are trapped inside a solid crystal, they can't fall to the bottom. They align themselves along the internal axis of the sapphire and grow into those microscopic rutile needles.
So the needles prove that the stone cooled naturally and slowly over millions of years. And if a modern laboratory takes that natural sapphire and blasts it in a high-temperature furnace to improve its color, a very common commercial treatment, what happens to the needles?
The heat of the furnace remelts the titanium back into the sapphire lattice. The sugar dissolves back into the hot tea. The needles disappear, leaving behind fuzzy, broken remnants. So when Koivula looks through his microscope and sees intact, perfectly formed rutile needles crossing each other, he knows with absolute certainty that the stone has never been subjected to artificial heat treatment by humans. The Himalayan tectonic crash is the only furnace that touched it.
It really is like each gemstone is a microscopic black box recorder recovered from an ancient geological plane crash. The collision happened tens of millions of years ago, but the flight data is all perfectly preserved right there in the crystal matrix, waiting for someone like Koivula to plug in the right fiber optic light and read it.
And reading that black box is more important now than it has ever been in the history of the gem trade. If we extrapolate into the future of analytical gemology, the industry is facing a tsunami of laboratory-grown gems and incredibly advanced, stealthy treatments.
It's a real problem.
We've reached a point where we can manufacture a sapphire in a controlled factory environment in a few weeks that has the exact same chemical composition, the exact same hardness, and the exact same refractive index as one that took millions of years to grow in Mogok.
A machine can duplicate the chemistry perfectly. But the factory sapphire didn't go through the continental train wreck. It wasn't dragged under Asia. It didn't experience the skarn forge of the Kabine granite. It didn't accidentally capture a droplet of ancient hydrothermal fluid.
Exactly. Well, let me rephrase that. It's more profound than just a chemical copy. The synthesis of macrogeological knowledge, understanding the violent mechanics of how Mogok formed, combined with the microvisual analysis established by Koivula, is the only reliable way to maintain truth and transparency in the gem world.
You need both.
The inclusions are the unforgeable signatures of natural Earth history. You can fake the color, you can fake the chemistry. You cannot fake a 45-million-year-old two-phase fluid inclusion.
But surely, given that humans have been mining the Mogok stone tract for centuries, literally since the days of the Burmese kings tunneling into those Ludwin caves, have we found everything there is to find? Has a winding valley given up all its secrets by now?
Not even close. Consider the starting point of our entire journey today. Johnkoivulaite, a complex barrel cousin with massive cesium atoms stuffed into its structural channels, was only identified as a completely new mineral species in 2019. That is incredibly recent.
Right. A guy sorting through gravel from the Painite mine finds a tiny, unrecognizable purple rock the size of a paperclip, and suddenly global science has a brand new species that requires a 100,000 atmosphere diamond anvil cell just to understand its high-pressure secrets. It proves the valley is still hiding things.
It proves that the geological complexity of the area is so deep So layered with different intrusive magmatic events and highly localized chemical anomalies like that wet painite skarn, that there are undoubtedly more unknown minerals waiting in the dark. We have only scratched the surface of the chemistry created by the Himalayan collision.
So to briefly recap this incredibly dense 45 million year journey, we started with a kid in Washington state finding a simple piece of quartz with some fool's gold trapped inside it. That kid, John Koivula, grows up to revolutionize an entire global industry by proving that the annoying flaws inside a gemstone are actually its most valuable scientific features.
He really did.
She throws out the hot incandescent bulbs, uses a cool, flexible fiber optic light to expose multi-million-dollar synthetic frauds and treated diamonds. And in return for saving the industry's transparency, the scientific community honors his legacy by naming a bizarre, boron-infused, color-shifting mineral after him, a mineral birthed in the unimaginably violent tectonic crash of the Mogok stone Tract, where pure limestone from a dead ocean was pulled into the mantle, baked into marble, and forged by molten granite blowtorches into the most precious, chaotic stones on Earth.
It is a profound reminder that knowledge is most valuable when it is understood and applied across different scales. The next time you hold a piece of jewelry, a ruby ring, a sapphire pendant, or even a simple piece of quartz, don't just look at the sparkle. Don't just see the surface polish that the jeweler put on it. Look deeper. Try to see the history. Look for the flaws that tell a billion-year-old story of continental drift and subterranean fire.
And I want to leave you with this idea to mull over as we sign off. We just spent an hour talking about a tiny 1.168 carat rock called johnkoivulaite that holds the highly specific, incredibly durable chemical signature of an entire ancient ocean floor being crushed by a colliding continent. If a rock that infinitesimally small can hold a story that massive and violent, what other invisible microscopic stories are sitting completely unnoticed in the mundane rocks right beneath your feet, right outside your door, just waiting for someone to point a flashlight at them and look a little closer? Because maybe the world around us isn't clean and pristine at all. Maybe the diagnostic muddy waters, the flaws, and the broken bits are where the real beauty hides.